In this bonus video, I'm going to be talking about this proof, actually the correlation of two random variables. Its absolute value should be between 0 and 1. I have given a proof of this in the regular lectures. Let's remember what this correlation is equal to. This is actually covariance of x and y divided by variance of x, variance of y, 1/2. So in absolute values, if this is the case, note that this quantity, the denominator is going to be always greater than 0 because we have variance terms, right, which are greater than 0. So this is this may be smaller than 0. So you can put it that way. Absolute value of this quantity is smaller than variance of x, variance of y in square root. And when we take the square of both sides, this is what we need to prove. So if we prove that, then automatically this will be the case. And actually, this is going to also lead to that the correlation is going to be between -1 and +1, because as I said, the numerator covariance can be negative or positive. Actually, before that, I'm going to prove another inequality. And both of these inequalities are actually related with the so-called Cauchy-Schwarz inequality. So let me write. I hope, yes, spelling is, I guess, correct. Schwarz is a bit tricky, yes. And this is an equality pretty much used in linear algebra. It basically says that if you have two vectors, right, then the dot product of these vectors, call these v and u vectors, right? So both v and u, let's say a vector, column vectors of n elements, then if you take the dot products of these two vectors and take the square, this is going to be smaller than taking the dot product by its own. So it's going to be the squared number of these vectors. You can also call this v square and u square. So in other words, this is what we have: v2 transpose times u is equal. So inner product of these two vectors is going to be smaller, equal to the product of the norm of these two vectors. Okay, so the application here, actually, I guess you can see the similarity here. So this is going to be the second derivation that I'm going to be doing. First, on the other hand, I'm going to show you again a similar expression, which is going to be expected value of x times y is going to be smaller or equal to, smaller than or equal to, again, let's square it, expected value of x squared times expected value of y squared. So this is going to be another application of Cauchy-Schwarz inequality. So first I'm going to give this proof here, then I'm going to give this proof. Well, actually, the idea is, well, there are different proofs for that, but I think the simplest one, and I think that's a pretty interesting one, is related with this one. So what we are going to do, the motivation here lies in defining a new random variable. Call this new random variable, for instance, z, let it be. So this is going to be, we would like a function of z, which is going to be a function of x and y, and it's going to consist of some square terms of x and y. And we would like this quantity to be necessarily non-zero. So what I mean is something like this. If I write an expression such as this one, now x and y are these random variables, and x minus alpha, this is going to be a parameter, and I'm going to consider, in the next step, I'm going to consider it as a random variable, but could now call it a single parameter. It doesn't matter the value. So since this is going to be a squared operation here, this is going to be necessarily greater than 0. So hence, expected value of z, which is going to be equal to expected value of x minus alpha y squared, is going to be necessarily greater than 0. So now let's go one step further. Now we have a quantity here which is going to be is equal to 0 or greater than 0. So it is necessarily non-negative, I should say. So anyway, let's go one step further. This is going to be equal to expected value of x squared plus minus 2 alpha x and y plus alpha square y square is greater than 0. Now let's use the linearity of the expectation operator, minus 2 alpha expectation xy plus alpha square expectation of y square is greater than 0. Now this actually, as you can see, these are, well, not exactly the same, but there is some hope that we can convert this to this this equation form here, or the inequality here. So how are we going to do that? Note that now this form is also a function of alpha. Up to this point, or at the very beginning, I assume that alpha is a parameter, but now at this point, I take alpha as a function. Why do I take that? Now here I take these as constants. Alpha y square, expected value of xy, expected value of x square. But for any alpha value, this is going to be necessarily greater than 0, because actually this is how we derive this. So at this point, now what I'm going to do is I'm going to replace this alpha by a convenient, or a combination of convenient terms, such that when I put this instead of those terms in alpha, I'm going to be obtaining this relation. If you actually examine this equation a little bit, you can easily see that if you replace alpha by expected value of xy, and note that we need this, right? Because we are going to have 1 here, and we are going to have a square of expected value of y square. So we are going to be obtaining this value divided by expected value of y square. This is going to work. So what I'm going to do is I'm going to put alpha here and alpha square, these values. So I'm going to have here expected value of x square minus 2 times expected value of xy divided by expected value of y square times expected value of xy. So we have a square here, and this handles the whole thing. Now we have the last term. This is going to be the expected value of xy again square, and we are going to have divided by expected value of y square, and there's going to be another square here, because note that we have square operation, times expected value of y square. These will cancel, and we are going to have expected value of xy square over expected y square, and the very same term, but it's going to be multiplied by 2 times here. So we go one step further. This is going to be, note that this is still greater than or equal to 0. Expected value of x square minus expected value of xy divided by expected value of y square is greater equals 0. Now, if you put this to this right-hand side and multiply by expected value of x square, we obtain this relation. Expected value of y square is going to be greater equal expected square. Anyway, so this is the relation that we have, that we aim to obtain at the very beginning, and as you can see, we have obtained this relation. Now a similar application here. This time we would like, actually the title of the bonus video was proving that correlation is going to be between -1 and +1. Therefore, we need to prove this. We are going to follow a similar strategy here, but note that now we need a covariance term. Applying this approach will not lead to a covariance term here. So I'm going to do a very similar thing. This time, just define it by this way. By the way, maybe we can use it with this sign, which means actually definition. So z is defined by this way. Now, at this point, I'm going to take the variance of z. Now, when we take the variance of both sides, note that this is actually a similar effect here, but note that we are going to have a covariance, hopefully, and that's going to be that's going to serve to my aim better. Anyway, when we take the variance, note that this is again greater than or equal to 0 because variance cannot be negative. So this term here, this inside is going to be equal to variance of x and minus 2 alpha covariance of xy plus alpha square variance of y is greater equals 0. We are going to follow a similar strategy here. Now the question is replace alpha with what value so that we are going to be obtaining this expression here. So alpha is going to be covariance of x and y divided by variance of y will work. So it's going to be variance of x minus 2 times covariance square xy divided by variance of y plus covariance square xy divided by variance y square and variance y. Again, this square will cancel. This is greater than 0. So the very same thing. So we have the same terms here, variance of x minus covariance square xy divided by variance y greater than 0. And we are going to obtain variance of x, variance of y greater equals covariance of x, y, which is again the same expression that we aim to obtain at the beginning. So since this expression is valid, therefore this expression is also valid.